Okay, welcome back. Happy Wednesday to you. If you've sent me an email in the past couple days and I've been slow to respond, I apologize. Yesterday, I took Nate, the 17-year-old, up to Utah State because he's thinking about going there. So we toured the campus, and it was actually pretty nice, and got a free meal in their all-you-can-eat buffet, which was cool too. We don't know whether he should take a tour of BYU because he's sort of been here before, but I don't know. Is that worth doing? Should he ride around in the golf cart? No, we're getting no from the audience. Not worth it.
Music, watching everybody like just stare at you for a while.
Yeah, it's kind of it's kind of like, I don't know if they do this still. I mean, back when missionaries used to go to the missionary training center, that you'd show up and they would put a little yellow or a little orange sticker on your lapel or whatever to indicate that you were the new guy. And it was a bizarre hazing ritual for for missionary service. Anyway, only time you'll ever get to ride in the golf cart. Go ahead and do it. So anyway, we've been talking about substitution reactions of alcohols. And just to review, our main problem with alcohols and substitution reactions is that the OH is a terrible leaving group. So if we want to use the alcohol as an electrophile, we need another strategy. We've got three useful strategies for substitution reactions with alcohols when we're dealing with stereocenters. Recall that PBr3 first turns the OH into a good leaving group, and then Br minus, which is liberated from PBr3 in the process, comes back immediately and acts as a nucleophile to do an SN2 reaction. I just wanted to mention something that came up in office hours today. This is the intermediate that forms. Br minus then acts as a nucleophile. I neglected to mention this last time. Br minus would not typically be on our list of things that's a good nucleophile. It's got a conjugate acid whose pKa is -9, and generally we've said the pKa of 0 or greater for conjugate acids is what makes a good nucleophile good. The halides in general are an exception to that. Iodide, bromide, and chloride are perfectly fine as nucleophiles. It has to do with their large size and polarizability. And we could say more about that, but it's not really necessary. You may just need to memorize them as exceptions to our rule. But in any case, that's why Br minus can act as a good nucleophile and do the SN2 reaction to get you your leaving group. So again, these reactions are generally first make a good leaving group, then do SN2. Same is true for SOCl2. The SOCl2 reagent happens to work better when you have a base. Pyridine is the base of choice, and that also gives you the alkyl chloride with inversion of configuration. Some of you have asked, is there any reason why you'd choose one versus the other? Not for our purposes. You can use them interchangeably, though in an actual lab there might be reasons you'd use one versus the other. Some reagents are water or air sensitive. Other reagents are expensive or have to be stored at low temperature. Some reagents might react with other things in a complicated molecule. So there are a lot of practical considerations for why you'd want more than one way to do one thing. But you can use either of these interchangeably. The third strategy we introduced at the very end of our lecture last time was a strategy that involved turning the OH into a good leaving group with a reagent called para-toluene sulfonyl chloride. And you do that without a subsequent SN2 reaction, which allows you to stop at this stage where the OH is a decent leaving group and pause indefinitely. This allows you to sort of avoid the inversion of configuration that happens when you go on and do an SN2 reaction with the bromide or with the chloride. The TSCl is sometimes called tosyl chloride. The automatic voice transcriber function on Zoom has had a crazy time trying to transcribe my words, especially words like tosyl chloride. It was like playing Mad Gabs, looking at the transcript to see what the heck I was talking about. Anyway, the real name is para-toluene sulfonyl chloride. And the mechanism of this reaction is very similar to the ones you saw above with PBr3 and with SOCl2. That is, the first step is that the oxygen acts as a nucleophile to make a new oxygen-sulfur bond and break a weaker sulfur-chlorine bond. You get an intermediate that looks like this, but instead of having the chloride that just left come in right away at first to do the SN2 chemistry, pyridine, the base, the non-nucleophilic base, removes the proton, the acidic proton on the positively charged oxygen, and then that gets you, sorry, I miswrote the product, that was a methyl group. That gets you to this product, the tosylate, with Cl- and the positively charged conjugate acid of pyridine, called pyridinium. And there is no going on to SN2 by Cl- at this stage. And if you ask why, I don't know. I really have no particular reason why para-toluene sulfonyl chloride should be able to stop here, whereas PBr3 wasn't and SOCl2 wasn't. So that may be a memorized detail. Okay, there are going to be things from this point on in OChem that you'll be able to work out based on first principles, and there will be other details that you will need to memorize. Nothing will save you from forgetting what a reagent does, except for your textbook on an exam that you can look at your notes and text. But when you have a limited amount of time, you probably want to spend as little of it as possible fanning through pages in panic trying to find something that you've forgotten. So it may be that you need some help remembering what reagents are and what they do. If this is you, then I recommend a couple of things. If you can do whatever works to memorize things. Some people like flashcards. You might consider making 3 different sets for any given reaction. Give a starting material and a reagent, and you have to draw the product. Given a starting material and a particular product, you say what the reagent would have been. And then given a reagent and a product, oops, I just need the arrow, reagent and a product, what would the starting material have been? This allows you to think of a reaction forward, backwards, in the middle, in between, and that will help you remember what a reagent does. You don't have to do it this way, but if you find yourself looking at practice problems right now at the back of the text and saying, what the heck does PBr3 do? I have no idea. Then that's something you need to fix. So there's a question on the chat. Can you then use the tosylate, that's what this product is called, as a starting material in a subsequent SN2 reaction? That's right. I realized as I was writing it that might be confusing. What I mean is that what I meant by no immediate SN2 there is that Cl-, unlike the SOCl2 reaction, Cl- does not come in and kick off the leaving group. So this tosylate can then be used subsequently to do all kinds of different things. And we illustrated when this might be useful with an example of stereochemistry. So imagine you have, and this material is not chiral, but there are stereochemical issues. Imagine you have this alcohol where the OH and the methyl group are cis to each other, and you want to make this azide where the methyl group and the OH are cis to each other. In that case, no problem. We talked about that last time. You could use PBr3 or SOCl2 to generate the inverted alkyl chloride, and then you could go on to do SN2 chemistry again. Wait a minute, PBr3 doesn't make the chloride, it makes the bromide. And then you could go on in a second step to add azide, and you would get, because of these two tandem SN2 reactions, you get two subsequent inversions, which gets you the stereochemistry that you want. In contrast, your strategy has to be different if instead of having the azide end up in an up orientation, cis to the methyl group, you want it to end up in a down orientation. And in that case, you can use toluene sulfonyl chloride and pyridine in step 1 to convert the OH into the tosylate, which you can abbreviate that way. Notice that we've turned it now into a decent leaving group that without touching stereochemistry. Then we can proceed to do the SN2 reaction with the azide, and we get only one inversion step. All right? Now, go ahead.
So OT acts as a good leaving group then?
OTS is the good leaving group. Yeah, that OTS, by the way, sorry, is the abbreviation for all of this. Equals. All right. Some have asked, what kind of reaction is the tosyl chloride and pyridine reaction? I hesitate to, it is a substitution reaction because what's getting substituted for what? Well, we're swapping out the chloro group on the sulfur for the alcohol group. So it's a substitution reaction at sulfur. But I'm afraid if we call it SN2, some of you are going to get mixed up having memorized that SN2 involves inversion of configuration and miss the whole point of using tosyl chloride in the first place, which is to turn OH into a good leaving group without inversion of configuration. So you can think of it as a substitution reaction at sulfur with oxygen as the nucleophile. But remember, the stereocenter doesn't change. All right, questions so far? All right. So now we need to switch to elimination reactions. Of course, any of these products from our 3 reactions that we just did, PBr3, SOCl2, and the tosylate, any of these products could be used as starting materials for E2 reactions. So, and you could use them interchangeably. That's why I'm not going to write out 3 separate reactions. I'm going to say you could use the chloride or the bromide or the tosylate, and you could do an E2 reaction. And in this case, you just have to use your E2 intuition to identify the beta protons that are beta to the leaving group and draw all the possible elimination products. So that's one strategy. Just use, do the substitution reaction on the alcohol first and then do an E2 reaction. That works, but we have a few more direct single step methods. Recalling that we can start with one starting material. I'm sorry, I guess I should have been more careful. We have various reagents that do this. I'm not going to rewrite them, see above. But we may want something that's not 2 steps, because every time you do a reaction actually in the lab, you not only have to do the reaction, but you have to clean it up and isolate the desired product from undesired side products. And it's expensive, and you lose a little bit every time you do a reaction. So doing things quicker and more efficiently in a smaller number of steps is often better. And in fact, to this day, if your lab can make a beautiful, complicated natural product in fewer steps than another famous lab can, you still get to publish that synthesis in a really great place, and then you get bragging rights, and there's a little bit of neener going on. You can ask folks in synthetic organic labs about this, but doing things in the shortest number of steps possible is kind of a way that organic chemists flex on each other. Did I use that term appropriately? Okay. I need help. We'll talk about these maybe later, but I need help with the term yeet and send. Used in interesting contexts in my household. And, yeah, for example, yeet is a verb. So the infinitive would be to yeet. And if we conjugate I yeet, you yeet, he, she, it yeets, we yeet, they yeet. And I guess if you want the formal second person plural like in Spanish, ye yeet. I don't know. Past participle, hath yote. Preterite, we yote. I don't know. Anyway, hath yitten. I just, if you could help me out with some of that stuff, that might be useful. But the best I can tell is used in my house. Yeeting can be throwing something and or. That's all I got. Any other definitions? Yeeted, yote, yacht. Yeah, never. Jake from State Farm says he never thought he'd find out the past tense of yeet from class. Yeah. We yote. Infinitive, we were yoting. I don't know. Okay, the joke's getting old. We need to move on. So anyway, if you can tell me if it doesn't mean to throw, if there's another definition, that might be useful to know. I was also informed last night that yeet is kind of a 2019 thing, so we should all move on, apparently. I don't know.
Google says an exclamation of excitement, approval, surprise, or all-around energy often is issued when doing a dance move or throwing something.
Okay. An exclamation of excitement when dancing or throwing something. Okay. So one could yeet while sending something? Yes, go ahead.
It's more about the feeling.
It's more about the feeling, okay. Okay, now I'm sorry, I'm singing the old classic rock song. It's more than a feeling. Didn't know that was about yeeting. Okay, we've gotten way off course, so we're going to send it by going back to elimination reactions of alcohols. And one of these can be done, and this is one your text highlights and spends quite a bit of time on. The problem is it's not that synthetically useful, and in fact, if you try to do this reaction on alcohols of any complexity, you generally turn your starting material into a thick, crunchy black tar, which is generally not what you want. Nevertheless, we will pretend that this reaction works, so as advertised, but beware of any reaction that tells you to use sulfuric acid as a reagent, and understand that there are probably a lot of either limitations or carefully controlled reaction conditions that allow this to happen. So the strategy with this elimination reaction is to convert the OH into a good leaving group by protonating it. So lone pair electrons, this is just acid-base chemistry. The pKa of sulfuric acid is very low, such that in aqueous solution, it's probably H3O plus that does the protonating. Nevertheless, we'll stick with what the text shows you. pKa of sulfuric acid is around -11. It's more than enough to convert the OH into the oxonium ion. Now, what happens next is troubling, because you might wonder, by analogy with what we did with HBr and HCl above, you might ask, why doesn't this conjugate base, which is the bisulfate anion, why doesn't that do substitution chemistry? And the answer is because your text doesn't show it, but it probably does happen at some level in solution. Nevertheless, we're going to ignore it. All right? I could give you some hand-wavy explanation about bisulfate not being a good nucleophile. There may be some truth to that, but I think I'm just going to say I don't know why it doesn't do SN2 at this stage. OH minus leaves. That gives us a carbocationic intermediate. And again, you might ask, well, fine, why doesn't bisulfate now do SN1? And again, the answer is it probably does. I don't know. But instead, we're going to show it removing one of the beta protons, doing E1 style elimination, alpha carbon, one of the beta protons, and that makes a new pi bond. Now, so in a lot of ways, this is a classic SN1/E1 reaction. The only thing we've added is this first step where we turn OH into a good leaving group. Then, from then on, it's leaving group leaves, and then the elimination step. Again, why don't we do SN1? And I need shrugging emoji because I don't know. There's probably a way for me to type it there. Now, so far we haven't really worried that much about equilibrium constant. We've just sort of assumed that the reactions we've been doing are downhill. This is one where the equilibrium constant is pretty close to 1. Oh, wow. This is a good one from the chat. I got to pause. We're back on Yeet. Colin from the chat says, okay, just one more. And thus the devil cheateth their souls and yeeteth them carefully down to hell. That's... Yes, go ahead. Sorry.
Just a quick question. Why does it go E1 and not E2?
Well, yeah, why does it go E1 and not E2? I don't know. I will show you. I'm not sure it happens soon. Let me look at the notes. Yes, it does happen soon. There is evidence that there's a carbocationic intermediate, so stay tuned. We'll get there in just a minute. Why doesn't it do E2 instead? Presumably it has to do with the fact that the pKa of sulfuric acid is -11, which means bisulfate is not that good of a base. So presumably it has to wait till you get the carbocation. All right. But the equilibrium constant here is close to 1. Each of these steps is reversible. And it's a comparison of bond strength, I think, would help see that. And especially if you accept that in aqueous solution, the acid is probably H3O plus instead. But in any case, the equilibrium constant is close to 1, which means you can actually start with the alkene and go backwards. We're going to do that in chapter 10. We're going to start with the alkene and go backwards. But for now, we're going to say that using some cute equilibrium strategies, we can isolate the desired product. Olefins or alkenes have lower boiling points than alcohols because they don't have hydrogen bonding interactions. And so we can actually set up an apparatus to distill off the olefin as it forms and then condense it in a separate flask. When you remove a product from an equilibrium reaction, that decreases the reverse rate of the reaction, and so the forward rate can win. And in that way, we can push all of our starting material to the alkene product. Okay. Caroline has asked, what stops the bisulfate ion from attacking the alpha carbon? It could. Why don't you get this SN1 reaction? I don't know. I've heard one of my colleagues say there is some evidence that can happen, but presumably it's not the most stable product. And in that case, and especially if you're distilling off this desired product, it may not matter whether you form any of the substitution product because you're pushing everything towards this alkene that you're removing. All right? Okay, so there's a complication with any time that you have a carbocationic intermediate that we have dutifully concealed from you to this point, but we're now pulling back the curtain on, and you're going to hate life just a little bit more in the next few minutes than you already do, and I apologize. Except it's kind of cool. So I don't apologize that much. Only a little. And to demonstrate this, I want to show you the results of some calculations you can do on carbocations. We've told you that primary carbocations are like crazy unstable, right? So if I were to draw, say, this carbocationic intermediate with a methyl group nearby, you would probably tell me that's not a good intermediate in a reaction, and I would tell you you are correct. If you try to calculate the energy of this structure in the gas phase, meaning by itself in a vacuum, and you do quantum mechanical calculations, and you optimize the structure, that's where you tell the program, you can move atoms around a little bit until you get the lowest energy structure. What this returns is an interesting and unusual structure in which one of the hydrogens from the methyl group is actually shared evenly between the two carbons of the carbocation. It's a bridging proton. It's like you've got a partial bond here and a partial bond there, and you've got a positive charge sort of shared in the middle. And if you look at what the orbitals look like for this molecule, there is the HOMO is actually a pi-type orbital that encompasses the hydrogen and the space below. And what it looks like, and again, this is not necessarily something you would have predicted, but it is something that the computations tell you is real. In some cases, for some carbocations, this bridged structure is more stable than the non-bridged structure. A little bit of nomenclature, a carbocation with an isolated positive charge is often called a carbenium ion. This is a conventional carbocation. And then one with a proton that bridges two carbons they call a carbonium ion because it's different from a regular carbenium ion. In a lot of ways, this is not that different from what I told you happens with carbocations anyway. If we were to look at this starting structure over here on the side, our conventional carbenium ion, we said there was an empty p orbital here, and we said that electrons from the carbon-hydrogen sigma bond were donating into the the empty p orbital on the positively charged carbon. And we said that the plus combination of that sigma bonding orbital with the empty p orbital next door, this is sigma plus p, would actually sort of look like the following. You'd sort of have a large lobe here, and it would taper off there, and another one there. So this is the hyperconjugation that's going on anyway in the conventional carbocation, and it's not too much of a stretch to imagine the hydrogen leaning over to be shared evenly between those two carbons, right? Anybody that's seen While You Were Sleeping, every time I say leaning, I think of a conversation with Joe Jr., because it looks like he's leaning. You maybe need to go watch it if you don't understand the reference. It's kind of a fun show. Anyway, so it's not a big stretch to imagine the hydrogen leaning over to get you to this carbonium ion. And frankly, it's not such a stretch to imagine the carbonium ion, the proton there, leaning over completely to now be on the other carbon. Where now our HOMO would look something like this, the sigma bond hyperconjugating into the empty p orbital on the positively charged carbon. Okay, and maybe you're asking, what the heck are you doing? And I don't really know, but what we're saying is that that positive charge can maybe be on carbon 1 and or carbon 2. And this process of, if we call the carbon that has the positive charge, what the heck were we doing there with wave function sign? That was uncomfortable. In the structure on the left, where the positive charge is on carbon 1, if we call that the alpha carbon and the adjacent one, the beta carbon, if you have a carbon-hydrogen bond on an alpha carbon, if you have a positive charge on the alpha carbon and a carbon-hydrogen bond on the beta carbon, that carbon-hydrogen bond can lean over and trade places. Yeah? How is it different from resonance? Remember, it's a great question. Resonance does not involve atoms moving. So the bridge carbonium ion, resonance structures there would be one where there's a double bond there, one where there's a pi bond, one where there's a sigma bond there, one where there's a sigma bond there, and one where there's a pi bond there. Those would all be resonance structures of each other. But when you move atoms now, you've got equilibria. And so the process of going from one carbocation or carbenium ion to another is called, appropriately, carbocation rearrangement. And it's an active area of controversy as to whether this carbonium ion is a transition state or intermediate. So you've got some, and this was an item of a lot of debate in 50 or 60 years ago, when high-level calculations were very difficult to do, and you had folks tweeting transition state, and you had other folks tweeting fake news, hashtag intermediate. And so it's just controversial, and it depends on the structure. For this particular carbocation, you can do the calculations, and the optimal structure is the carbonium ion. But from now on, anytime you see a carbocation, you need to be aware of the possibility for carbocation rearrangement. So let me show you an example where that has occurred. So here is an alcohol. we'll call carbon 1, 2, 3, and 4. And let's say we want to use H2SO4. It turns out we don't need a huge amount of H2SO4. Anybody who may have been paying attention might have noticed that, I wasn't paying attention so I didn't notice, but might have noticed that we regenerate our acid in the final step. So you don't actually need a full equivalent of H2SO4, you just need a catalytic amount. Anytime you're using sulfuric acid, water is your solvent because you get concentrated sulfuric acid in water. The product observed for this reaction, the product you expect for this reaction, is one in which the double bond is between carbons 1 and 2, right? Because we should turn the OH into a good leaving group, and then the leaving group should leave to give you this carbocation, and then you should do the elimination reaction because you only have one kind of beta proton. There's no protons on the other beta carbon. But unexpectedly, and in addition, we also observe some strange other structures. What the heck is going on? Do we even have the right number of carbons there? So counting carbons is a good idea when you're dealing with unexpected reactions. We have 4, and then there's 2 other methyl groups on carbon 3. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So we haven't lost or gained any carbons. These are all isomers of each other. What's happened? Well, let's look at this carbenium ion, this carbocation. If the bisulfate ion, or if water acting as a base, removes this proton, we get the unrearranged product. But let's dig in a little bit deeper, looking at the carbocation. Here's methyl group, here's the hydrogen, here's the positive charge. This is our alpha carbon, and this is one of our beta carbons. Then here you've got a methyl group and 2 other methyl groups. And this is our other beta carbon. So what's going on? Just like a proton, a carbon-hydrogen bond can lean over, so can a carbon-carbon bond lean over. In fact, in this structure, we're already doing carbon-carbon sigma bond to P hyperconjugation. And if we were to draw the sigma plus P orbital that comes from that, it would look something like this. There would be another lobe on the other side of carbon, but I'm just simplifying it. And so it would not be too much of a stretch for the methyl group to lean over to get a bridged carbonium ion intermediate. Or perhaps even transition state. This is one of the reasons they call this intermediate carbonium ion, because that's a carbon that's sort of bonded to 5 things. You thought we couldn't have those. They're sometimes high energy intermediates. And then if the methyl group continues to lean, let's see what we've got then. We would have CH3 here, CH3 here, CH3, CH3, proton, and our positive charge would be there. Okay, you see what we've done? We've taken a bond that was hyperconjugating into an empty orbital. We've moved it in between the alpha and the beta carbons, and then we kept moving it so that we formed a new bond with the carbon formerly known as alpha, because now the positive charge is on a different carbon. All right? Again, it may help us to number the atoms like we did above. 1, 2, 3, 4. We continue that process here. 3, 4. In this intermediate carbonium ion, either transition state or intermediate, the methyl group is shared evenly between 2 and 3. In the final carbocation, the methyl group is shared between, the methyl group is on carbon 2 instead. And this is our rearranged carbocation. All right, questions so far? Go ahead.
Is it possible, so you can only rearrange the methyl group if it's on a beta carbon, or can you do it from farther?
Yeah, the question is, can you only rearrange with either by moving a proton or a methyl group or some other alkyl group if it's on the beta carbon? Yes. Okay. You have only things beta, just like with elimination reactions, only things beta can do this. Go ahead.
How would we see this in a benzene ring then?
How would we see this in a benzene ring? I don't know.
Like, is it possible at all?
I think you're asking about a 6-membered ring,
Yeah.
and yes, you can.
And it would only be able to do it to the 2 carbon betas to it?
Yes, it would only be able to, the groups that move, whether proton, alkyl, or CH3, have to be beta to the positive charge. Yeah, go ahead.
Could we then do the same thing and bring the positive charge onto carbon 4?
Could you then, yeah, good question. Now notice that from this rearranged carbocation where the positive charge is on 3, you've got all new kinds of beta carbons. We could definitely go back the other way. Oops. But one question you could ask is, could you, on a plane with the mouse or on a train, no, would you be able to have this CH bond lean over? Okay. Sure, theoretically, why would that be not a good idea here? Look at the structure of the resulting carbocation. Where would the positive charge be if this proton leaned over? It would be on a primary carbon, which is pretty unstable. So generally, you're not going to do rearrangements. I'm just going to draw briefly what we were talking about. Imagine this proton leans over. Recording? We're still recording. I just accidentally pressed escape, which made it. Huh.
You just have to delete it. It happens on that.
I have to do what?
You just have to close the window. It just happens on max when you have the top.
But I don't want to close the window.
No, just for your email, and then it goes.
Oh, okay. Yeah, we do need to close one. Sorry about that, folks at home. We're having a temporary challenge. And I'm not, okay, good. I'm going to reshare my screen. And I think we're back. Okay. Yeah, let's just imagine that this proton leans over, is shared, and then goes here. Then the positive charge is going to be there. That's a primary carbocation, and that's unstable. So that would be too far uphill to go.
Okay.
But this brings out an important point. What do you notice about our starting carbocation with the positive charge on carbon 2? What kind of carbocation is that? Secondary carbocation. Over here, what kind of, the rearranged carbocation, what kind of carbocation is that? Tertiary. more or less stable, well, I'm already writing the answer, so leading the witness, more or less, what on earth does that mean? More stable. So rearrangement happens when you can convert a less stable secondary carbocation into a more stable tertiary carbocation. Now it happens in different situations than that. And so all of a sudden, as you're trying to ponder the consequences of this little revelation, how do I know when I'm going to do carbocation rearrangement? You're going to look for it anytime you have a secondary carbocation adjacent to a tertiary or a quaternary carbon. Okay? Either of those situations allow you to convert a less stable secondary carbocation into a more stable tertiary one. Now, there are other situations when it can occur, but that's where I want you to be looking for it. Now that we've drawn the rearranged carbocation, I'm going to just draw it in a slightly simpler way. Now you can see where the other weird products come from. I have a beta proton there and a beta proton here. If I remove the red beta proton, I end up with this product. If I remove the purple beta proton, I end up with this more stable, more substituted product. Now, experimentally, I probably find that this is the major product. All I will ask you to do when carbocation rearrangement happens is to select both the unrearranged products and the rearranged ones. Okay. This process of carbocation rearrangement of leaning over plays an important role in the biosynthesis of cholesterol. And I'm not prepared to draw that structure for you immediately, but I'll take you through it next time. It's a cascade of carbocation rearrangements. Sometimes we call these carbocation rearrangements 1,2 methyl shifts, because the methyl group leaned over from one carbon to the adjacent one. Or we might call it a 1,2 hydride shift, because the hydrogen leans over with its electrons and shifts places. So why did we look for carbocation rearrangement? Because we saw an intermediate in which there was a tertiary carbocation adjacent to a quaternary carbon. And you can see other situations for carbocation rearrangements. There are other examples of situations where carbocation rearrangements occur. All right, questions you want to ask about that? I feel like I'm remembering a complicated carbocation rearrangement problem from your text, and I'm trying to think about what it might have been. Yeah, I'm not going to make up that problem from scratch. What if we wanted to do an elimination reaction on alcohols, but we didn't want to mess with the whole carbocation rearrangement thing? We didn't want a mix of products. We've got a solution, and that is a strategy of E2 style elimination of alcohols with no carbocationic intermediate. And that's the reagent that we'll talk about next time. That's POCl3. People like to call it POCL. But that will help you do an elimination reaction without having any carbocation rearrangement. With that, I will send you forth into the world to go yeet your homework. No, I'm sorry. Anyway, see you next time. And thank you for the help on yeet.